Exercise 1.4. First question, you are given some operations. We want to check whether binary or not. That's the question. Now, you recall when the operation is said to be binary, you take two members from the set on which the operation is defined and find A star B. It should be again in the same set. If this is true for every members, then it is called binary. Now, question number 1. First question, on Z plus, that means positive integers. Remember, Z means all integer, plus means positive integers, and star is given by A star B equals to A minus B. Now, we already discussed this. If you remember, this is indirectly subtraction. So if I take 1 and 2 from Z plus, again I'm emphasizing Z plus means positive integers. Now you apply the operation 1 minus 2, you know minus 1, which is not in Z plus. So therefore you can say that asterisk is not a binary operation. Not a binary operation. Not a binary operation. One example is sufficient, remember. Second, again on Z plus, I repeat one more time, Z plus means only positive integers like natural numbers, and star is by A asterisk B equals to AB. This is, you know, indirectly just multiplication, which also we have discussed. So clearly, if I take any 2 from Z plus positive integers, and if I multiply them, that is A into B, which is A star B, which is also in Z plus, product of two positive integers is always a positive integer, and therefore you can say that here asterisk is a binary operation. Is a binary operation. I'll go to third question, number 3, on real numbers on R. Star by this A star B equals to AB square. A star B equals to AB square. Now for every two real numbers, you know, square is also a real number, product is also a real number. So for every AB belongs to R, clearly AB square also in R, because if you have a real number, if you square this, which is a real number, if you multiply these two, which is also a real number. So therefore you can say that asterisk is a binary operation. Is a binary operation. So this way we can check whether given operation is binary or not. In question number 2, you are asked for 3 things. First, check for binary, then commutative, whether it is a commutative or not, and third one, associative or not. You are asked for 3 things. So before you check for these 2 properties, you need to see whether it is a binary or not. So let's see the first question on Z. On Z means all integers, remember, positive integers, 0 and negative integers. You are given star by this A asterisk B equals to A minus B. This is a standard subtraction operation, you know. So clearly, for every A, B from Z, if you take any 2 integers, if you find A asterisk B, which is their subtraction, A minus B, which is always in Z. Here remember, this can be 0 or positive or negative, so it is always in Z. In previous question it was Z plus, here it is Z, remember. So you can say that here asterisk equals to subtraction is a binary. Once it is a binary, you can check the other two properties. Now you know very well that if I take 1 and 2 from Z, it implies if I find 1 minus 2, it is not same as 2 minus 1. So here you can say that A asterisk B is not same as B asterisk A. One example is sufficient, remember. Therefore asterisk is non-commutative. You know it, subtraction is never commutative. Non-commutative, not commutative. In subtraction, order is important, so this is non-commutative. Now you take 3 numbers, even it will not be associative also. If I take 1, 2 and 3, any 3 numbers you can choose. You find 1 minus 2 minus 3, and you find 1 minus 2 minus 3. Your answer is minus 1, so this will be 2. What about this? This is minus 1 and minus 3, so this is minus 4. Obviously these two are not equal. Minus 1, minus 3, minus 4. This is minus 1, so these become plus 1. So therefore star is non-associative, not associative. This is very standard operation. So by just observing the operation, even you can say that it is not commutative, non-associative. Now I'll go to second sub question on Q, that is on rational numbers. A star B equals to, you are given AB plus 1. A star B equals to AB plus 1. So here you take any two rational numbers for every AB from Q. Obviously A into B is also a rational number. If I write plus 1, which is also a rational number, so you can say that this is again in Q. Product of two rational number is a rational number, plus 1 if you do, it is again a rational number, so it is in Q. So what's the conclusion? Asterisk is a binary operation. Once it is a binary, then and then you can check the other two properties. Now next, that is commutative property. So A asterisk B, if you find it is AB plus 1. If I find B asterisk A, it will be BA plus 1. Now BA and AB both are same in product, so from this you can say that A asterisk B equals to B asterisk A, and this is true for every AB, remember, in Q. And therefore what's the conclusion? Asterisk is commutative. It's a commutative. Asterisk is commutative. So commutativity holds here. The next one is your associativity property. So third property for the same question, associativity. So you need 3 members. So for A, B, C belongs to Q, rational numbers. We'll find A asterisk B asterisk C. We'll find this. Now what is A asterisk B? You are given that it is AB plus 1 asterisk C. A asterisk B, you are given AB plus 1. So I will just place the value. Now consider this is like A and this is like B. So this would be, what's the definition of asterisk? This into this plus 1. So AB plus 1 into C plus 1. I repeat, what is A asterisk B? First product plus 1. AB plus 1. This is A, this is B. So A into B plus 1. A is this entire bracket. Now we just open the bracket. So A, B, C plus C plus 1. This is 1. On the other side, now we find A asterisk B asterisk C. So first we apply operation for this A asterisk as it is. What is B asterisk C? Which is B into C plus 1. This into this plus 1. That's the definition. What is A asterisk B again? That is A into B plus 1. This into this plus 1. So B into C plus 1. Now this is A, this is B. What is the definition? This into this plus 1. A into, this is our B. A into B plus 1. So if I open the bracket, ABC plus A plus 1. You see, these two are not equal. You notice from 1 and 2, these two are not equal. So A asterisk B asterisk C is not equals to A asterisk B asterisk C. So therefore, this is non-associative, not associative, non-associative. You can take one example also. For example, you find 1 star 2 star 3. Find this. Let's see. This also you can give the answer. What is 1 star 2? That is 1 into 2, 2 plus 1. So 3 star 3. What is 3 star 3? That is 3 into 3, 9 plus 1. So 10. Now I'll find 1 star 2 star 3. What is the answer to this? That is 1 star 2 into 3, 6 plus 1, 7. Now what is this? 1 into 7 plus 1, which is 8. These two are not equal. So therefore you can say that here asterisk is non-associative. You can give by one example also. This is a general proof. Here this will do if it is non-associative. I'll go to now 5th sub question on Z plus, that is again positive integers. Here A asterisk B is A raised to B. So this is a positive integer, this is a positive integer. So for every A, B belongs to Z plus, if I find A asterisk B, which is A raised to B, integer raised to integer, which is also an integer, so this belongs to Z plus again. So therefore asterisk is a binary operation, is a binary operation. This would be a binary operation, because if I find here in the question that integer raised to integer, here this is an integer, this is integer, so in turn this is also a positive integer, so it's a binary operation. Now for commutativity, you take for example 1 asterisk 2. What is that? 1 raised to 2, which is 1. Find 2 asterisk 1. What is that? 2 raised to 1. 2 raised to 1. This number raised to this number, remember. 1 raised to 2. Here 2 raised to 1, which is 2. So what's the conclusion? 1 asterisk 2 is not same as 2 asterisk 1. And therefore this asterisk operation is non-commutative. It's non-commutative. Now what about associativity? You find 2 star 3 star 4. You can choose any 3 numbers. From definition itself, if it's a one type of power function, so obviously it has to be non-commutative as well as non-associative. To find this, if I apply here 2 raised to 3 star 4, what is 2 raised to 3? Which is 8. So 8 star 4. What is 8 star 4? That is 8 raised to 4. This number raised to this number. Go to this 2 star 3 star 4. 2 star as it is. What is 3 star 4? 3 raised to 4. 3 raised to 4. So this is 2 star. 3 raised to 4 is nothing but 81. So what is 2 star 81? That is 2 raised to 81. You see these two numbers are obviously different. 8 raised to 4 is not same as 2 raised to 81. So therefore you can say that this is not equals to this, and therefore here asterisk is non-associative. It's non-associative. Next question, question number 3. So question number 3, you are given a set here which consisting of 1, 2, 3, 4 and 5. An operation here that a asterisk b equals to, you are given a, the symbol b, equals to minimum of a and b. Here m stands for minimum of these two numbers. Now we are going to prepare the table here. So 1, 2, 3, 4, 5. Column wise 1, 2, 3, 4, 5. Now we just prepare a table like this here. So here operation is asterisk equals to minimum. So if I prepare the table here, 1 asterisk 1, that is the minimum of 1 and 1, which is 1. Minimum of 1 and 2, this 2, that is 1. Minimum of 1 and 3, 1. Minimum of 1 and 4, 1. Minimum of 1 and 5, 1. With this you take one by one all these members. 1 asterisk 1, asterisk means minimum here. 1 minimum 1, 1. 1 and this, which is minimum 1. Minimum of 1 and 3, 1. Minimum of 1 and 4, 1. Minimum of 1 and 5, 5. Now with 2 you take each of this. So what's the minimum of 2 and 1? 1. Minimum of 2 and 2, 2. Minimum of 2 and 3, 2. Minimum of 2 and 4, 2. Minimum of 2 and 5, again 2. Go to this now. 3 with each of this. Minimum of 3 and 1, 1. Minimum of 3 and 2, 2. Minimum of 3 and 3, 3. Minimum of 3 and 4, 3. Minimum of 3 and 5, 5. Same way with 4 you take each of this. 4 asterisk 1, 1. 4 and 2, 2. 4 and 3, minimum is 3. 4 and 4, minimum is 4. 4 and 5, minimum is 4. Now with 5 you take each of this. Minimum of 5 and 1, 1. Minimum of 5 and 2, 2. Minimum of 5 and 3, 3. Minimum of 5 and 4, 4. Minimum of 5 and 5 is 5. So this way we can prepare the table in such questions. This is sometimes called composition or multiplication table. Here we can prepare the table like this. Here, sorry, this is my mistake. Minimum of 3 and 5 is 3, not 5. Let's correct it. So you are just asked to prepare this table in this question. Write the operation table of the operation this. So we have just prepared the table. You can answer, this is not asked, but you can answer such questions. Suppose I want to find 1 made this, made 3. So what is 1 made this 2? So minimum of this is 1 here. This one 3. So what's the minimum of this? So answer is 1. If I find this, 1 made 2 made 3. So here 1 made as it is. What is 2 made 3? It is 2. What is 1 made 2? It is 1. That way you can answer such questions. In this question you are asked just for this table only. Now in the fourth question, question number 4, one table is already there. You want to compute this. Ready table is given in the question. So the first question is compute 2 asterisk 3 asterisk 4. So let's go to table. First from table we find 2 asterisk 3 and then asterisk 4. So let's go to table. You want 2 asterisk 3. So 2 asterisk 3, if you look at it, is 1. So answer to here, 2 asterisk 3 is 1. Then 1 asterisk 4. So 1 from here and 4 from here. 1 asterisk 4. So it is 1. So that way we write this value. So 2 asterisk 3, as I explained the table, it is 1. This asterisk as it is, 4 as it is. Now again go back to table as I explained. 1 asterisk 4, if you go to table, the answer is 1. So the value of this expression is 1. One more you are asked. 2 asterisk 3 asterisk 4. 2 asterisk as it is. What is 3 asterisk 4? You go to table, you will realize 3 asterisk 4, it will be 1. Just go to table, you will see 3 asterisk 4, it is 1 in the table. Now 2 asterisk 1. So 2 asterisk 1, again if you go to table, it is 1. So both the expressions are having the same value. The next question is commutative? Is asterisk commutative? That's the question. Now if you look at table carefully, you will see that for every AB from set say A, you find A asterisk B, you find B asterisk A, you will notice that the both are always equal. This is always true. Or if you look at table, given table, it's like a matrix. So around diagonal, this portion and this portion will be same. This entry and this entry. So indirectly it's a symmetric matrix, so it has to be commutative. So answer is it's a commutative. It's a commutative operation. It's a symmetric matrix indirectly if you look at it. So question number 5 to 8, try yourselves. Not a big task. It is about LCM and HCF. I'll go to question number 9, which is very important question for the entire exercise. You are given some operations on Q, you know, that is on set of rational numbers, and you are asked which of these binary operations are commutative and associative. So you are asked for these two things. First, whether they are commutative or not, as we did in the beginning. They are associative or not. For these two questions you are asked for each of this. So let's see the first question. All are on Q. A asterisk B is A minus B. Now again, this is very standard subtraction operation. So you know answer to this. 2 minus 3 minus 1. It is in, you know, it's minus 1. It's obviously in Q. If I find 3 minus 2, that's 1. So are they equal? No. So 2 minus 3 is not equals to 3 minus 2. So therefore here asterisk is non-commutative. It's non-commutative. Same way you can try. You try 1 minus 2 minus 3, which will not be same as 1 minus 2 minus 3. So therefore asterisk is non-associative also. Non-associative. Right? We did it, so I'm not emphasizing on this. A asterisk B equals to A square plus B square. So if you find B asterisk A, then it would be B square plus A square. And obviously here these two are equal. So A asterisk B equals to B asterisk A. So therefore your what's the conclusion? Asterisk is commutative. It's commutative. Now here, being a square, associativity seems to be doubtful. Let's find 1 star 2 star 3 here. So what is 1 star 2? That is 1 square plus 2 square, which is 4 star 3. Now this is 5 star 3. So this is 25 plus 9. Definition is a square plus b square. So you know this is 34. If I get this 1 star 2 star 3. 1 star, what is 2 star 3? It is 4 plus 9. 9 plus 4, which is 13. So 1 star 13. Now what is this? 1 square plus 13 square. This is 170, you know. So immediately your conclusion is these and these are not equal. So asterisk is not associative. Non-associative. Question number 10, that is, you are asked for identity. Find identity for star defined on question number 9. So I'll go to, for example, first question. There again a asterisk b equals to a minus b. Now you recall, if identity equals to e, then you must have a asterisk b, e equals to a asterisk a equals to a. It means that these two should be same. Indirectly it means it should be, asterisk should be commutative. Here you already noted that this is non-commutative, so you can say that there is no e such that a asterisk e equals to a asterisk a equals to a. So therefore identity doesn't exist here. Identity does not exist. You know it, for subtraction you cannot find such member. Identity element here doesn't exist. Now second question, if you go to here, next question, let's see, a asterisk b equals to a square plus b square. Let identity equals to e, so we try to find e here. So by definition, as I explained in one of the earlier session, a star e has to be a. Even reverse is also true. E star a should be a again. Now what is a star e? Which is a square plus e square equals to a. What is a star e? That is a square plus e square. Now from this you cannot get e. E cannot be obtained. E cannot be obtained. So again, in this case, identity doesn't exist. Identity E doesn't exist. Question number 11. Here A is n cross n, that is positive integers cross positive integers. So you have ordered pairs of integers like this. Here a comma b, such that a and b both are natural numbers, remember, ordered pairs. Now here star is by this, you need to take two ordered pairs, a comma b asterisk c comma d. Definition is just to add them, a plus c comma b plus d. This is the definition, first with first comma second with second addition. Now commutativity and associativity, you will try commutative and associativity. You try for these two properties. I'll go for identity. identity. So let's take, let identity E equals to E1 comma E2. Now if E is identity, you must have A comma B asterisk E1 comma E2. So answer has to be same, A comma B. We want to find this is a question. Now what is this? This is A plus E1 comma B plus E2 equals to A comma B. Now you compare them. So A plus E1 equals to A, B plus E2 has to be B. So we'll get the E1 equals to 0, E2 equals to 0. So E1 comma E2, which is 0 comma 0. But this is not in n cross n, remember. Not in n cross n. So here again we say that identity E does not exist.